Welcome to yet another physics video. In today's video we're looking at Unit 2 Physics, Area Study 1, How's Motion Understood. Our topic is force vectors in 2D. And in this video we'll be looking at the resolution, the addition and subtraction of force vectors. Our first task is to resolve the force vectors A and B into vertical and horizontal components. So we can see force A is a magnitude of 60 newtons at an angle of 45 degrees from the x-axis. And likewise, vector B has a magnitude of 40 newtons and its direction is 30 degrees from the x-axis. And we want to resolve or break them up into their horizontal and vertical components. So first of all, the vertical components, we see that vector A can be considered as having a vertical component, which is effective in the y direction from our xy coordinates. And vector B has also a vertical component, smaller in size. Likewise, there is a horizontal component for both these vectors A and B, and we've labelled that force A in the x direction and force B in the x direction. Now some simple trigonometry. We know that with a right angle triangle, if we know the force magnitude F and we know the angle theta, we can calculate the component in the y direction as F sine theta and the component in the x direction as F cos theta. We're going to use that throughout this particular video. So first of all, the vertical component of force A, it's going to be force A sine theta, which is 60 times sine of 45. It gives us a value of 42.4 newtons. So force A, its vertical component in the direction y is 42.4 newtons. Likewise, force A in the horizontal component, labelled force AX, has a value of 60 cosine 45. It also comes out to 42.4 newtons. Now this should be no surprise, as a triangle with 45 degrees generates an isosceles triangle where these two side lengths should be equal. Let's look at force B. Likewise, its vertical component, force BY, is 20 newtons because it's 40 times sine of 30, and its horizontal component, FBX, is going to be 40 cosine 30, and it comes out to 34.6 newtons. So this is how we use a right angle triangle with the simple trig rules to resolve or break down any particular vector into its vertical and horizontal components. So to visualize this, we can represent a 60 Newton force at an angle of 45 for the horizontal into a vertical component of 42.4 newtons and into a horizontal component of 42.4 newtons also, and a 40 Newton force in a direction of 30 degrees from the horizontal as having a vertical component of 20 newtons and a horizontal component to the right of 34.6 newtons. Task number 2, we want to calculate A plus B. We're going to add these two vectors together. We want to work out the magnitude and the angle. So first of all, let's look at one technique where we're going to do this as a visual technique. We've got our vertical components first of all, as you can see. Force A has a vertical component of 42.4 and force B has a vertical component of 20. So we can add those two together to work out the overall or the net vertical force. Now remember, when we're adding vectors, we always add them tail to tip, okay, which means if I'm adding vector B to vector A here, at the end of the tip of A, I add the tail of B. Likewise, vertically, at the end of the tip of A, I add the tail of B. So let's do that. Let's move force B over on top of force A. So that's the vector sum of those two, tail to tip. And we see that adds up to a net vertical force of 62.4 newtons. Likewise, let's look at the horizontal components. A has a horizontal component of 42.4 newtons to the left. B has a horizontal component of 34.6 newtons to the right. Let's add these two together. Again, we always add our vectors tail to tip, tail to tip. We add that across, and we get a net force of 7.8 newtons. So looking at these two components, we have a horizontal of 7.8 newtons to the left and a vertical of 62.4 newtons upwards. We add them together and we get the net force. There is an alternative technique or method called matrices addition. And several of my students have been using this because they're studying more advanced maths and they like this technique. First of all, a matrix is a bracket filled with data. In this example for matrix A, their value for x, which is the horizontal component, is 42.4. Notice we put in negative because in terms of a Cartesian coordinate, this is actually a negative in the x direction. And vertically, we're going up in a positive direction, that's 42.4. So that's vector A represented in a matrix form with the x term first and the y term second. Likewise, we can do the same with vector B. Vector B has an x component of 34.6 and a y component of 20, both of which are in the positive quadrant. So if we want to add them together, we simply add the terms. So the x term for vector A, negative 42.4, is added to the x term for vector B, 34.6, and that gives me an end result of negative 7.8. So here's our 7.8 negative towards the left, as we did previously. Likewise, the y term for vector A was 42.4, and the y term for vector B was 20. Add them together, we get 62.4. And that was the vertical components. A nifty technique to add two vectors in a quick way using matrices. Regardless of our technique, we end up with a right angle triangle. We have one side length of 62.4, another side length of 7.8, and we want to work out what the hypotenuse is. So we can use Pythagoras' theorem. So we substitute in our values. The vertical was 62.4 and we square it. The horizontal was 7.8 and we square it, and we take the square root of that particular sum. And we end up with a net force with a magnitude of 62.9 newtons. We also wish to state our angle. So here's our internal angle from the x-axis, and we're using a tan function. This angle is an opposite side length against an adjacent side length using that ratio. So 62.4 over 7.8. Now to find the angle theta, we take the inverse of tan of that particular ratio. We end up with an angle of 82.9 degrees. So there's our internal angle of 82.9 degrees. So the answer for task 2 is when we add vector A and vector B, we end up with a resultant vector of 62.9 newtons at an angle of 82.9 degrees from the negative direction of the x-axis. X-axis here, here's our positive direction of the x, here's our negative direction. Task number 3, we want to calculate vector A, take away vector B. Let's do a similar process to our previous one. So our vertical components, we can see again, we've got the same two vertical components, but this time we're going to take them away. It's force A vertical component, take force B vertical component. With vectors, we don't take away. What we do is we add the negative of the vector. So here's our original vertical force B, and that's the negative of force B in the vertical component. So now we can simply add those two together. Force A in the vertical plus the negative of force B. And again, we still follow the convention of tail to tip. So I take that, and at the tip of force A in the vertical, I add the tail of minus force B in the vertical. So that is my tip to tail. So we add those two together, and we end up with an overall vector in the vertical of 22.4 newtons upwards. Let's do the horizontal. Again, here's our two horizontal components for force A and force B. To work out our net force in the horizontal, we want to take the horizontal force of A and from that subtract the horizontal force of B, which by the way is again the same as adding the negative of the horizontal force of B. So let's do that visually. There's our negative. It's exactly the same magnitude, but instead of pointing to the right, it's pointing to the left. Again, we add our tail to tip. We move that across. So we're adding the tail of the negative BX to the tip of the positive AX. Do that and we end up with a net force of 77 newtons to the left. So there's our vertical component and our horizontal component placed together. And that's our net force. Once again, we can look at this in terms of matrices again, but now we're doing a subtraction. Let's follow the technique. So force vector A can be described as having a horizontal component in the x direction of negative 42.4. That's in the x direction, but it's moving to the left, which is the negative section for the x. And it's got a vertical component of 42.4 going up. 42.4 going up. That's for A. Our matrix for B is a positive 34.6 in the x and a positive 20 in the y. Now to take them away, we again just take the elements. The x component from vector A, and we're going to take away the x component from vector y. Negative 42.4, take away a further 34.6, gives me a total of negative 77. And 42.4, take away 20, gives me 22.4. So the negative 77 just means our x component starts at 0 and it goes 77 units to the left. And our positive 22.4 means it starts at a y of 0 and goes up 22.4. Let's work out our final magnitude and angle. Once again, we have a right angle triangle with a side length of 22.4 and another side length of 77, and we're after the hypotenuse. This is a right angle triangle, so we can use Pythagoras' theorem to work out the magnitude of the hypotenuse. So the net force is 22.4 squared plus 77 squared, all square rooted, gives us a value of 80.2 newtons. And finally, the angle. The angle is identified here between the x-axis and the net force. We're using tan function because our original values were an opposite side length and an adjacent side length. We substitute those in, we take the inverse of the tan, and we find the angle is 16.2 degrees. So our final result when we subtract force vector B from force vector A is a net force of 80.2 newtons at an angle of 16.2 degrees from the negative direction of the x-axis. We can check our results using the Physics simulator. First of all, I have set the vector magnitude as 40 and I've set the angle of inclination as 30 degrees. So here's vector A with a magnitude of 40 at an angle of 30. We see there's a y component of 20 and an x component of 34.6 as we calculated earlier. Let's also try this for vector A. Likewise, vector A had a magnitude of 60 and I'm using in this simulator an angle of 135. The Physics simulator for vector components measures from the x-axis, so we go around 90 plus another 45. In our calculation we measured it as 45 from the x. We're now looking at an angle of 135 from the positive x-axis. We do this and the vertical component of force A was 42.4 and the horizontal component of force A was 42.4, exactly the same as our calculation. Let's now look at adding and subtracting these two vectors. Once again, we'll fill in our data for vector A and vector B. Let's look at this. We have vector A with a magnitude of 60, and in this simulator an angle of 135, which is the 180 take 45, gives us 135. And vector B has a magnitude of 40 and an angle of 30. We add these two vectors together, and we see the addition of vector A and vector B results in a magnitude of 62.91 meters at an angle of 97.11 degrees counterclockwise from the positive x-axis. So if I move 97.11 degrees counterclockwise from the positive x-axis, I have an angle of 82.9 degrees remaining to the negative x-axis. Likewise, if we subtract force vector B from force vector A, we end up with a magnitude of 80.26 meters at an angle of 163.78 degrees, which is measured counterclockwise from the positive x-axis. So we can see here the 163.78. Now if I take that from 180, once again I end up with an angle roughly of 16.2 degrees, the same as our calculations.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.